So, but it still doesn't explain the properties, why these semiconductors are exhibiting the characteristic property. To understand that, we will have to understand a little bit of quantum mechanics. Whenever I say quantum mechanics, a lot of engineering students feel, put off. I mean, they're scared. They don't know that. They're not familiar. So it can sound a little difficult, but it's not that difficult. And if you want to understand semiconductor devices thoroughly, it is essential to have some basic knowledge of quantum mechanics. After all, if you look at today's devices, uh, the MOSFETs that are being fabricated, let's say in the Intel or TSMC fabs today, they're called a 7 nanometer technology. So that means the dimensions of the devices are about sub in the nanometer scale. So when you go to the nanometer scale, it is essential to apply the laws of quantum mechanics. Without that, you cannot explain the properties. So for the rest of the lecture, I'll just introduce a few basic concepts in quantum mechanics. Please bear with me, and it will become clearer, why these are important. So before we get into that, why quantum mechanics? Why not simple classical mechanics, the age-old one, the laws that Newton gave us in 1600s? Well, yeah, that works. Newton's laws are, of course, they're laws, they work. But they work at the macroscopic scale. For example, if I want to compute the trajectory of a car, let's say I know the position and velocity of a car, and I know how much, let's say I'm pushing it and I apply certain force on that, I know how much distance it travels, right? Or I can take, any macroscopic, for example, planets. I know, the force that is applying on, it's acting on the planet. I know what is the position and I know what is the speed with which it's moving. So I can compute the orbit of the planet. So these are all laws of classical mechanics. And one of the important features of classical mechanics is that the measurement outcomes are predictable, by which we mean that if we know the initial conditions and we know the force, we can compute the trajectory entirely predictable. I mean, there's no there is no probability in that. So as I said, this classical mechanics works, very well for the macroscopic world. But the moment you try to go into the microscopic dimensions, I said nanometers. How much is a nanometer? For example, if you take your human hair, the one strand of hair from your head, the diameter of that strand is a couple of microns, right? Microns means 1,000th of a millimeter. So one single strand of human hair is 1 micron, and 1 nanometer is 1,000 times smaller than that. So imagine we are really going into the atomic dimensions now, right? So when we go into such very, very small scales, we need to, the classical mechanics doesn't work anymore, and we have to talk about a probabilistic description known as quantum mechanics. What we do in quantum mechanics is, instead of talking about a particle, for example, electron, I won't talk about electron. I'll talk of a wave function associated with an electron. A wave function is simply, a quantity which has, x and let's say, if you take up one dimensions, x and time dependence, the position and time dependence. So it's a function. I could talk of it like, sine kx, and I could also put a time dependence I omega t or something like that. I can do that. So this is a simple wave function that essentially tells you that the probability, it gives you the probability. We will see that in a moment. So wave function is used to describe the particle, and how the particle moves is actually given by what is known as Schrodinger equation. We will come to that in the next slide. But Schrodinger equation is essentially an analog of the Newton's second law. Essentially, it tells you once you know the wave function at a particular position and at a particular time, how does a wave function evolve? So that can be calculated using Schrodinger equation. So the important part we need to note is that the measurement outcomes in quantum mechanics are probabilistic, by which we mean that we cannot accurately, with 100% certainty, tell that electron is going to be at this position. We can only say, okay, electron will have about 90% probability of being in position X and 10% probability of finding it somewhere else, right? So that is what is, a probabilistic description. So we cannot accurately tell. And the length scale where quantum mechanics is useful is given by what is known as de Broglie wavelength. We will talk about this as well. All right, let's get into it. So the first thing is, de Broglie's wavelength we mentioned. So this is one of the foundational principles of quantum mechanics. Back in 1924, a French physicist by name Louis de Broglie, he hypothesized that matter exhibits a wave-like behavior. It is somewhat counterintuitive to us because we are used to thinking of a matter as particle. For example, a ball, an electron, or proton, and something like that. This we think of them as particles, but it turns out that they also have a wave-like character, by which we mean that it will be described by a probability wave. So if you have a classical particle, I will say that, okay, it's moving from position 1 to position 2. Instead of saying that, I'll say in the wave-like description, it has a probability wave, and the probability wave has a maximum amplitude at its position 1, and then after a certain time, it has a maximum amplitude at position 2. So the probability is changing, the wave function is changing. That is essentially what is called a wave-like behavior. So de Broglie said that the wavelength of matter wave, for example, an electron, could be given by simply Planck's constant divided by the momentum of the electron. So the de Broglie relation tells you that the wavelength is h by p. P is the momentum, h is the Planck's constant. All right, how does this help us? Well, it is somewhat, if you might remember your classical, your high school physics, wherein you might have studied about how, a string which is supported by two rigid supports, right? Just you could imagine these two, black colored lines as the rigid support, and I put a string between them and I pluck it. Right? What happens? You might have studied that this string, the way it oscillates, it cannot oscillate at any wavelength or any frequency, but it has to oscillate at a certain discrete frequency given by the distance between the nodes. For example, here, it can only have those wavelengths for which, only those wavelengths for which L equal to n times lambda, by which we mean that the distance between the supports has to be an integral multiple of the wavelength. Only those wavelengths are supported. For example, here you have one particular red line, which is having the exact wavelength equal to L. So that's why this is allowed. Whereas if you look at the blue line has wavelength longer than L. That's why that cannot be supported. It has to be an integral multiple. Okay, that won't happen here. And that is why this blue, sort of a wave is not supported. So something similar happens in atoms or microscopic scale. The origin of this, why this was required, came about when physicists started studying how light is emitted from heated gases. For example, if you take some sodium and heat it up as heated sodium gas, and you look at the emission from that, it turned out that the emission was actually not any wavelength of light, but it was certain discrete wavelengths of light. And by measuring the wavelength of the emitted light from hot gases, you could actually predict what type of gas was there in that. So scientists were puzzled by it because this sort of a behavior could not be explained by by classical mechanics. So they tried to analyze this, the Morse model and all that came about. So wherein basically the hypothesis was that if you have an electron which is going around a nucleus, so it cannot take any orbit it wants. It has to take only certain discrete orbits for which the circumference of the orbit, 2 pi r, is an integral multiple of the wavelength. This is not the regular wavelength, but de Broglie wavelength. So for example, if you're talking of an electron, it could only take those orbits where the circumference is basically n times de Broglie wavelength. So here I'm showing you two particular orbits. I think these are 6 and 4 wavelengths. You could check it up, but essentially you can only have integral, and n is an integer here. N is integer. Only these orbits are supported. So this is an important characteristic, and this was actually very useful for explaining how those, I mentioned the discrete emission lines from hot gases. So this was very useful. I mean, you might have studied Lyman-Balmer series and so on in physics in your +2. Well, yeah, that comes from here. All right, so fine, de Broglie wavelength is important, but let us try to estimate how much is de Broglie wavelength. Okay, that gives us an idea about when quantum mechanics is important. So for this, you have a problem here. So the problem is to calculate the de Broglie wavelength when the velocity of an electron is given by 10 power 5 meters per second. So what is the de Broglie wavelength? Let's just try to do that. So we know that de Broglie wavelength lambda is basically h by p. So I'll try to first compute p. P is simply the momentum, which is simply mass times velocity. So the mass of electron is 9.1 into 10 power minus 31. Okay, I'm not writing the units. You should always make sure that the units are consistent. Velocity is 10 power 5 meters per second, and that will turn out to be 9.1 into 10 power minus 26 kg meters per second. Right. Right. So this is the velocity. This is the momentum. So the de Broglie wavelength will be simply Planck's constant, 6.63 into 10 power minus 34 divided by the momentum. So which is 9.1 into 10 power minus 26. So it turns out that, if you just, I did this just before this. So this is approximately 7.3 into 10 power minus 9 meters. All right. So what this is telling us is that de Broglie wavelength is, sorry, I shouldn't do that. I wanted to highlight. So de Broglie wavelength is a very small quantity. All right. So we don't have to worry about quantum behavior when your length scales are larger than that. If you're talking about, movement of a car on a highway, the length is, meters. So we don't care, meters and kilometers. We don't have to apply quantum mechanics at all. But if you're talking about propagation of electron in a semiconductor, in a MOSFET, the MOSFET size itself is, I said, 5 nanometers or 7 nanometers, let's say, typically, then we have to apply quantum mechanics. Okay. So I would also like to write the de Broglie relation in a slightly different form. So instead of this, I will write it as, let me say, P is equal to h by lambda. So instead of doing this, I'll just rewrite it. I'll simply divide and multiply by 2 pi. So if I do that, this particular quantity, h by 2 pi, is known as h cross or h bar. Okay, this is again another fundamental constant. It's convenient to use this h bar sometimes. And 2 pi by lambda is called as wave vector k. Wave vector k. Okay. It will become clearer later why we call it a wave vector. But for now, we are saying that, de Broglie relation essentially you could rewrite like this. So instead of writing, lambda equal to h by p, I'll say p is equal to h cross k. Okay. I will use this again later. That's why I just want you to remember this. This is one form of writing momentum. All right. So, all right. So now we understand that, at what lengths quantum mechanics has to be applied. But then we have to start applying the Schrodinger equation, and we will do that now.